Consider the sequence AN defined as, so we got AN, if our index is odd, AN is equal to 1 over n squared. If the index is even, it's minus 1 over n cubed. Show that the alternating series, okay, it's definitely alternating because the minus, it goes plus minus, but show that the alternating series, adding up these ANs, fails the conditions of the alternating series test, but still show that it converges. Okay? So this is an important thing to understand. The alternating series test, or AST, I sometimes refer to it as sort of a half test, because the only thing you can ever get out of it is convergence. Okay? You only get that your series converges from the alternating series test. And to use the alternating series test, you have to know things about AN, or rather, typically BN, which is the absolute value of the sequence. Right? You have to show that the limit goes to 0, and that eventually, at least, the BNs are decreasing. So BN plus 1 is not bigger than BN, and so on. Okay? So those are the two things. And if they don't hold, then the alternating series test fails or doesn't apply. But some people think, okay, because the alternating series test gives you convergence, that if you can't use it, if the BNs their limit doesn't go to 0, or they're not decreasing, if for whatever reason one of those two conditions fails, then automatically the alternating series test is telling you that you diverge. Okay? That's simply not the case. Okay? Just because the alternating series test doesn't apply doesn't mean you get to conclude divergence. Nothing involving the alternating series test can do anything other than show convergence. Now, it is true, if the BNs, if their limit isn't 0, you'll get divergence, but not because the alternating series test fails, but more a consequence of the nth term test. Okay? So in this case, yeah, allegedly, the alternating series test won't apply to these ANs, but we should be able to show convergence. Okay, so what are we going to have to do? Well, we'll have to show that one of the AST conditions fails. Obviously, if it is going to converge, we know it's got to be that decreasing condition, so we'll focus on that. But we also need to show convergence. Now, this series, just to better understand it, starting at 1, you get 1 over 1 squared, and then it'll be plus negative, so we'll say minus 1 over 2 cubed, plus 1 over 3 squared, because we're back to an odd index, and then minus 1 over 4 cubed, so that's 64, and then 1 over 25, and then the next one will be minus 1 over 2016. Make these 2's look a little better. And then we'll be back up to 1 over 49. So we can sort of imagine what this series here looks like. And it definitely is alternating. That's not in dispute. So let's... we've got two things to do. We can show that this converges. That's something we have to do. But we can also investigate the alternating series test and see why it fails. I think I'm going to start with the alternating series test part and show why it fails. So for the alternating series test, so I'll just remind myself the ANs here, 1 over n squared if n is odd, and minus, that's the alternating part, if minus 1 over n cubed if n is even. So for the alternating series test, as I say, you work with these BNs, which are just the absolute value of the ANs. So we just throw some absolute value bars around everything over here. Now, obviously, 1 over n squared is already positive, so that doesn't change. And then the minus 1 over n cubed, well, that just becomes the positive version. So it still is sort of switching back and forth between being the reciprocal of the squares and reciprocal of the cubes. But that's our BNs. Okay? Now, I should point out that... again, this isn't relevant to showing the alternating series test fails, if in this case it does converge, but it's important to sort of think theoretically. Okay, if you know that the ANs will converge, which is what we want to show, but not through the alternating series test, well, then that means that the limit of the ANs goes to 0. But if the ANs are going to 0, the absolute value of the ANs will also go to 0. So it should be the case that the BNs here, if we investigate it, the limit of the BNs will go to 0. Okay? That should not be the point of failure ever. If the alternating series test fails to apply, but eventually your series converges, then it's the alternating series test will fail because of the decreasing condition. So a little bit of theory to think about. But for the sake of completion, or just to really illustrate that, yeah, let's go through and check. But again, this shouldn't really be something we need to check. Okay? So the limit of the BNs, is that really 0? Well, notice that the BNs are maybe the nicest way to write this is 1 over n squared is the biggest the bn's can be. Sometimes they actually are. And 1 over n cubed is the smallest the bn's can be. Bn's alternate, switch back and forth between which we're working with. So, of course, they're sandwiched between the two. And 1 over n cubed is obviously less than or equal to 1 over n squared for positive n's. Okay, but hold on. The limit as n gets bigger of 1 over n cubed is 0. Well, same thing with the limit of 1 over n squared. And so by squeeze theorem, if you really, really had to sort of write this up nice and neat, so by squeeze theorem, the limit of the bn's will also have to go to 0. Okay. Since, again, the 1 over n squareds tend to 0, and the 1 over n cubes tend to 0 as n gets bigger. Okay. So, yep, we do get a 0 here. The limit this condition is true, so it's got to be the other condition that fails. Okay, so let's actually go through, and that's the thing that we're really going to have to take a look at. So how could it fail? So the second condition that we need to show, or rather that shouldn't be able to be shown, is that eventually the bn's here are decreasing. Right? It doesn't have to happen right away. You can have a little bit of wiggle room at the start, but this needs to be true eventually. Okay? So you might say for all n after a certain point, after some point. All right, so we need to have this decreasing condition. Obviously, if the AST is going to fail, and we've already shown, if you didn't believe my sort of argument over here based on the nature of the question, but obviously if we've already shown the limit of the bn's is 0 and the AST fails, it's got to fail this. So how do you fail this? Okay? What does failure look like? So what we need to show this doesn't hold. It's not that you have to flip it around. It's not that the bn's have to be less than the bn plus 1s all the time. That isn't something that should necessarily be true. It's that the bn's are less than the bn plus 1s sort of infinitely often. The farther you go out, you'll still be able to find times where the sequence jumps up a little bit. You know, maybe it's decreasing, 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 but if it's always decreasing, then this condition will be true. All it's got to do is just bump up once every few terms. And then this doesn't hold, okay? But they're still all heading down towards 0. Okay? At least that's how I visualize it in my head. So we need, to show this doesn't hold, we need this to happen, let's say, infinitely often. It can't just happen a few times, because then if you went further out, maybe everything is just decreasing. So how are we going to do that? Well, the fact that the sequence switches from 1 over n squareds to 1 over n cubes is the key, because as I was saying earlier, the 1 over n cubes are way less than the 1 over n squareds after a certain point. Well, actually, pretty quickly, I think. Okay? And so, okay, you're big, and then the next term will be really small, but then you jump back up to something that's big, back when n is odd. And so I think that's the key. I think eventually, possibly even almost immediately, an even bn is followed by an odd bn that is going to be much bigger. I think that's what we can show. Okay, so let's say something like, let's consider bn where n is even. Specifically, we could say n is 2 times some number, because even numbers are just multiples of 2. Okay. Then the next term would be something that's odd. Oops, sorry, n plus 1 is odd, which would be 2k plus 1. Well, we have formulas. If you know that your index is even, b2k is 1 over 2k cubed. So that would be 1 over 8k cubed. And then the next term, 1 over 2k plus 1, that'll be 1 over, we square our odd term. Okay. Now, that should be bigger than this. But you might say, well, how should I justify that? Should I set up some sort of inequality where I show that this square, I'm just expanding out the square, by the way, should I show that that happens and you know, do some more calculations and show that that happens as long as k is bigger than 100, so it definitely happens infinitely often. Is that the sort of argument we should make? You probably could get away with inequalities like this. Just looking at this, though, I think rearranging it, you'd probably have to start working with a cubic expression, and I don't think that's the smarter thing to do. So I think instead what we're going to do to show that this inequality does hold, like I'm not hiding from that inequality, but I think algebra is not necessarily the way to go about doing it. So here's what I would write. I would say, notice that the limit as k tends to infinity, as k keeps getting bigger and bigger, 4k squared plus 4k plus 1, so the square of 2k plus 1, the square of my odd n, my n plus 1 there, over 8 cubed is 0. Right? We know this just from our knowledge of limits of rational expressions. If the degree on top is less than the degree on bottom, we know that limit exists and is 0. But let's think about what that means. That means that this expression here is getting closer and closer to 0, and after a certain point, it'll always be within whatever distance you want for 0. You could even use the formal definition of a limit to show that, if you wanted to. Okay? But what we can do is we can say, okay, because of this, okay, we know that eventually, or if you want to be formal, you could pick some actual k, capital K, so that k is past that, make the following true. If you wanted to make sort of a rigorous formal argument, but I'm just gonna be a little loose here. So we know that eventually this expression here has to be less than 1. Because if you're going to 0, you can't keep being big like 1 or 2 forever. You got to start getting within a half, getting within a third. So eventually, for k is big enough, this will happen. But if we rearrange it, divide both sides by 4k squared plus 4k plus 1, which is positive, so the inequality sign does not need to flip around, we have this, but that's bn, and we see that bn is less than bn plus 1, which is the wrong thing. So it looks like after a certain point, to summarize, so what this shows, so eventually we can see that b for an even is less than b for an odd, so the bn's are not going to always be decreasing. Now, it would be true that b odd, the next term, is less than that as well. But the bn's are not decreasing, and that is the other condition of the AST, and that one clearly fails. Right? We don't have that. We don't have that they're decreasing, so the bn's are not decreasing. So we can conclude, okay, for the alternating series test, while it is true that the limit of the bn's is 0, which we didn't really need to justify if we had done the convergence part of this question before, but that's true. So that is true, but the bn's decreasing is not true. So the alternating series test fails to apply, which is probably the best way to say it. Don't just say fails, because then your mind might say, okay, so it fails to converge, therefore diverge. No, the alternating series test just isn't part of the conversation. It doesn't work here. It doesn't apply. Okay? So, all right, that's step 1 of the question done. They said, show that the alternating series test won't apply. But we still will get convergence. Why? So let's again look at our sequence. It's 1, and then minus cubes, and then you add on 1 over squares, and then minus cubes again, right? But if you look at these, right, each of the odd terms is 1 over n squared. And we know some of the 1 over n squareds converges because it's a p-series. It's a p-series with p equals 2, which is bigger than 1. And what have we got here? The even terms, well, we're subtracting, but that's not going to matter in a moment, but 1 over n cubed, and we know that that's also a p-series that converges because p is 3 in this case, which is greater than 1. Now you might say, yeah, but what about the minus sign? Maybe that's doing something. Well, let's get rid of the minus signs. Right? We know, thanks to the absolute convergence theorem, that if we can show that the absolute value of the ANs converges, then the ANs themselves converge, which is what we want to try and show. So, once again, we can just use the absolute value of the ANs, they're 1 over n squared, or 1 over n cubed, because these are just our BNs from before. But you can definitely say, okay, well, they're clearly less than 1 over n squared. The sum of 1 over n squared converges. As we said, it's a p-series, p equals 2 and greater than 1. And so, because the absolute values are less than 1 over n squared, you can say by the comparison theorem, or comparison test, sorry, we can see, well, if the bigger one converges, then the smaller one, in this case the absolute values, must converge. It's not 0, it's a 1. And then the absolute convergence theorem, or absolute convergence tells us that, yeah, the ANs converge. In fact, they absolutely converge, but that's not really required here. So we use we said the AST doesn't work, but the ACT in this case it does. So we get that our ANs do converge. Again, it's not 0. It's infinity. Or 1 to infinity. Okay. So there we go. A little rough. I could have written it up a little nicer and neater, but I like looking at this because it's more about sort of behavior and sort of feeling out why the AST doesn't work. And why it is because we're alternating between two sequences that are getting small enough. They are getting small enough so that the sum converges. But one is getting noticeably smaller than the other. And so that causes the AST to fail because the sequence is sort of, it's going down. They're both going down, but one is, maybe a better visualization would be this. The odd ones, they're going down towards 0. They're getting smaller. But the other ones are, the even ones are just dropping like crazy. Like they're really far down. And so the AST requires that everything go down nice and smoothly. Whereas here, even though everything's getting small enough to converge, it's bouncing back and forth, and that oscillation is what fails. So the AST doesn't apply, but this does converge, and it's an excellent example of that.